Everyone, my name is Fan Zhang. So first, please forgive my voice, and I've having bad cold this week. So if any possible, sneezing, coughing during the talk, just please forgive me. I tested it's not COVID yesterday, but if you feel not very comfortable, like too late, you are starting with me now. So I'm also the Archivedi Schmidt AI and Science postdoc fellow, and today my talk is about the self-supervised learning and the robot learning in the simulation. So basically, this is like the pipeline of the talk today. I will basically introduce a little bit of my research to better explain that why do I want to show the self-supervised learning or the robot learning in the simulation. So basically, and then the second part will be the robot simulation and then the robot learning in the simulation. And then the last two parts will be about the self-supervised learning and also some examples of our research in the self-supervised learning with the robotics. So this is like a very general introduction of the whole robot learning or the self-supervised learning. Just like a quick introduction of myself. Some of you have seen these slides before, but just a quick introduction of myself. So basically, I did my PhD in the Imperial College London, followed by around 2 years of postdoc, and then this 1 year of the postdoctoral fellowship. So basically, I work on robotics. This is some of my work, and also the works in the lab. Like we are basically working on how using the machine learning or the deep learning so the robots can work with or for human. So here are some examples. Like for example, like the first one is like a wheelchair. We have like multiple wheelchairs in the lab, and one of the applications is how the children with disabilities can use this wheelchair to follow the adults to different places. And also we have the iCub robot from the IIT, and this is how it learns to play the piano, and also like how the robots can like communicate with people in the hospital. This is some with the augmented reality with how to use the AR to control the robot for the grasping. And we recently bought the spot robot from the Boston Dynamics, and one application is like we are using this robot to mapping the whole map of the building, and then so the robot can do the different navigation in the whole building. And the last one is like one of my work is not very related to the robots, but we are basically using the motion capture system. Like we put the cameras on the ceilings, and we use the motion capture system to get the dancing data of the dancers, and we accordingly provide like different feedbacks for the dancer, like how to improve their dancing skill, or like what's the level of their dancing. Is it like professional or beginning? Like this kind of feedbacks. My main works is about the robot-assisted dressing. So the idea is like we want the robot to dress the patients who completely lost their upper limb functionality. So basically, like we designed this whole robot pipeline following this certified nursing assistance practice test guidance. So this CNA test is a compulsory test in US. And part of the test is actually asking the nurse to dress these mannequins. And this mannequins is used to simulate the adult paralyzed patients who cannot move both of their arms at all. And we basically designed the robot pipeline following this real pipeline. Like there will be 4 stages. Like first, the robot will be located randomly in the room, and then the robot will move to the hanger, grasp the hospital gown on the hanger, and then the robot will fully unfold the gown in the air, and then the robot will move around the bed to dress both arms of the mannequin. And to do this, like there are a lot of like manipulation problem here. So basically, we call it like deformable manipulation because the clothes is deformable, and it increases the difficulty of the manipulation for the robots. So basically, we have 2 manipulation problem here. So the first one is how to actually unfold the garment. So the first method we have here is like we have the garment here, and we want to kind of like locate the grasping area on both sides of the garment. So the problem turns to like kind of like perception problem, like how do we actually locate the grasping area? So basically, one method here is we call it like the pre-grasp manipulation. So basically, we define different. We want to like predict different grasping location, orientation, and different grasping primitive, and we use the deep Q learning from demonstration to do that. So the input data will be the RGB images, multi-view RGB images of the garment. So from the real setup, like we use the robot to grasp the hanger, and we use the robot to keep rotating the hanger to get the multi-view images. And for the in the simulation, and this is also like what I want to talk about the most like today, like the simulation. Like we put cameras around the garment to get the multi-view images of the garment. So this is a bit more details. So we can see like how we get data in the real setup. Like the robot will keep rotating the garment, and then in the simulation, like the garment will just fall down based on the simulated gravity, and we use all these cameras around the garment to get the multi-view images of the garment.
Can I ask, what are the demonstrations, like simulated like operation, or you like manually operate your physical robotic arm, or like you said, learn from demonstrations, or the simulated demonstrations, or real world demonstrations?
So basically, we have both here. Like we use this to get the RGBD images, and we will also try to learn like where the robot should grasp the garment, what's the orientation and what's the primitive. So we will learn all the things together in the network.
But who's like the demonstration is like like manually operating with a joystick, that like robotic arm, and then you want to make the system operate like a human operating.
Yeah. So basically, from the simulation here, we basically like have the data, and we will manually choose like where the robot should grasp, and then in the simulation, you just program the robot to grasp there. This is like how you collect the demonstration data, and after you have the demonstration data, you kind of like initialize the whole network, and then you do the Q learning based on the initialized network to actively grasp, get the data.
So from your simulation, you decide how the robot will grasp data. You feed that to the robotic arm. The robotic arm does that. If it's a success, then it's positive reinforcement.
Well, yes. So basically, you train all of this in the simulation first, yes, and then you fine tune with the real data.
Okay.
Yes.
When you actually fine tune the real data, you mean the robotic arm that has been trained on the simulation will actually pick up the dressing down. If it does it successfully without dropping, then that's a positive reinforcement to the network.
You mean in the simulation, or you're talking about the reinforcement learning part?
So in the other image you had in the next slide,
Yeah.
So that one, top one, is the camera simulation, right? Where you're trying to figure out what is the best angle to pick up.
Yes.
This down below is where, based on that simulation, the robot is actually picking up.
Yes. So
right?
I will show more here. So basically, to answer your question, first is so basically like we have the cameras all of here, and then we decide like where to grasp, and even in the simulation the robot will try to grasp it and to see if it's success or not. And like you said, if it succeeds, you get like one as a reward, otherwise it will be 0. And then you train everything in the simulation first, and then based on this trained network you do in the real robot real close again.
But how good is the arm just based on the simulation training?
So the grasping, so it's based on where do you grasp. So it's like a position and orientation. So it actually doesn't matter with the robot arm. As long as you have the same gripper, the kinematics part is done by the robot part. It's not like in the, like you are not learning the whole motion. You are learning where to grasp the clothes and how to grasp the clothes.
Okay. But so you said it's first done in the simulation and then done in real
Yes.
time? If you don't do if you only do the simulation bit, is it good at finding where to grasp?
That's actually what I want to present today. Like, why do we need the simulation, and why do we do the sim to real learning? Because in most cases, like not just my research, but like in general, like the people who work on the simulation now, especially in the robots area, they will find like even you train a network and it works like quite well in the simulation, and then now you have some like real data. Most cases it will not work. That's why people need to do this sim to real learning, fine tune with the real data. But in the meanwhile, they will find like if you do everything from the real setup from the scratch, then you need a lot of time to do the like collecting data training. So that's why people always train with some simulation first. So this is kind of like a trade-off between the simulation and the real, but which I will show more details today. Yes. So the second part related to the close manipulation is we do another way of unfolding the garment. So we're like thinking like how human actually unfold the garment. Like in many scenarios, they will not try to find where is the corner, where is the sleeve opening, but they will just like trying to kind of like slide along the garment edge to fully unfold the garment. So basically, we want to do the same with the robots here. We put the tactile sensors on the gripper of the robot. So this is the images from the tactile sensor. So actually, from the image, we can kind of like see where is the garment edge. And we also put the camera like in front of the robot. So you also get like RGB images of the clothes. And then what we do here is like based on the input of the tactile images and the RGB images, we want to learn like at each time step like how the robot should move to unfold the garment. So basically here like the input will be this multimodal images, the tactile images and RGB images. And then basically in the latent space, we will learn this latent model here. So basically give the current tactile image and the RGB image, we project into the latent space, and we have the action here, and we will have the next state in the latent space here. And then we will also, like from the latent space, we will like predict the next step of the images here. So basically the whole network is following like a conditional variational autoencoder here. And for the learning part, we basically like have the current images. We have like some candidate actions, and we define some cost functions, and we will choose the best action here. So I mean, this part will be not the main talk today, but what I want to show here is, as you asked before, like why do we work on the simulation? Is because especially for the clothes deformation with the robots, like even for one clothes, if you want to grasp it or like unfold it, it's something like very challenging. Like no works in the real robot now. Like no groups in the real robot now saying, okay, our robots can do the thing, whole like shirt folding thing autonomously now. You can either do it with some teleoperation, or you like based on a specific clothes, you say, okay, I can do the unfolding or folding with this clothes, but you cannot do the general folding and not all the unfolding. So that's why we usually, in the robots area, like people usually use the simulation to train everything first. And then they will fine tune with the real clothes, real robot based on their scenario. And similar for me here, like basically, I use this Blender engine to do the clothes simulation. I use so we will simulate the clothes deformation in this Blender engine. And then we'll collect data, train the robot's policy, and then fine tune with the real robot and real clothes. So basically, this will introduce my like next part of the talk, like the general introduction about the robot simulation and the robot learning in the simulation. So basically, like when we talk about the robot simulation, we talk about like from two perspectives. One is the special purpose of the robot automation. So this part of the robots is usually used in the factory. Because in the factory, you actually don't need the robot to learn something. Like as long as the robot is precise enough to do some like very precise manipulation in some specific application, it is good enough. And that's also like why in the robots area, like in the early research, like basically in the industry or manufacturing areas, is the only area that the robots can make profits because it will easily reduce a lot of cost for the factory. But now, like we generally talk about the general purpose of the robots. So the idea is like we want the robot to kind of like work with people or for people in either the home or the hospital scenario. And we are dealing with some general purpose manipulation. So like here I show some examples. So we have like how the robot will serving people, how to cooking, or even the unfolding the shirt or the dressing. This is kind of like the general purpose of the robots. So that's where the robot learning plays a very significant role here. So this is the video from 2015 from the Dapper Robotics Challenge. So at that time, this was the most advanced humanoid robots at that time. And if you look at the papers, they are always like, okay, we have like very good success rate. We did that, we do that. And then, okay, the developers say, well, let's have a challenge thing here. So this is 2015. The interesting thing is like they designed a series of manipulation tasks, manipulation local or motion tasks. No robots finished the task at that time. They all have all different problems here. So which means to actually realize this general purpose robot autonomy is very, very challenging. But from 2015, like we already have like make a lot of progress. So this one you might see like from the OpenAI, they do the robot to manipulate the Rubik cube. But even with this, like they cannot do the actual reasoning. It's more like from the manipulation part. Like they need something to reason, like how to, like where to, like which side to change the Rubik cube, and then the robot only do the manipulation part.
So the learning agent will say right clockwise, top, anti-clockwise, and then the robot will follow the instruction and do it.
Yes. So the robot only do the manipulation part. Like so, you have another reasoning thing. And you say, okay, now we should move, like say, let's go say like clockwise. So the robots here only do is how to move it clockwise. And this is also like kind of like controversial, like when they just release the video because they make it like very vague, saying, okay, the robot can now do the Rubik cube. But then a lot of discussions and they say, okay, like we are actually doing only the manipulation part. This is like the this robot called Animal. It starts from the ETH, and now they build a company for that. And now it's doing very well in the locomotion right now. They have tests in different terrains for the locomotion. And same with the grasping. And now they even make some grasping, as you can see here, like one is for the grasping and one is for the suction. And then they use this kind of grippers to do different grasping tasks here. And also now is like a very good time for the robot learning because we have the deep learning and it's indeed like solve many problems that cannot be done with robot before. And we also have like a lot of good and relatively cheap robot hardware now. For example, this Panda robot is like around, I don't know, like 40K or something. Compared to before, it's much cheaper. And we also have a lot of computing power now. And for the robot learning, is basically, we can say it's basically two parts. The first part is robot perception, and the second part is how you actually do the decision making, the manipulation. And for the robot perception, we can also like have all different several methods. So here are some very typical ones. So the first one is the 2D object detection. So basically, it's like you give like RGB images. You want to do some either the detection or segmentation with the image. And we have like many methods like mask, RC, and the YOLO to do it. This is the 2D. And then people say, okay, like how do we do the 3D data? So we usually use this point cloud. So basically, like for the RGBD camera, like it will not only give you a 2D image, they also give you a point cloud. And the point cloud is like each point presents the x, y, z positions of that point in the point cloud. So basically, you get a 3D data of what the robot sees. And then in the 3D data processing, they also have like different point net plus, like different networks to just focusing on the 3D data processing. And also like now here, like they do the multi-modal data, like not only the image, but also some other signal. They do the multi-modal data understanding. And then for this tool, it's like, in the beginning, like people will use the LSTM or other methods to do the sequence of images processing. Now they do the transformer with the attention architectures using only a series of images. And also here are different methods. Like for example, we have like self-supervised learning, which I'm going to mainly talk today. And also like here, a lot of people will work on how to use the synthetic data to do the robot perception, which I'm also going to talk later. So the second part is the robot decision making. This is like how, after the perception, how robot will actually move. We also have like different methods. Like reinforcement learning is definitely like one of the biggest parts now. Like a lot of people with robots work on the reinforcement learning. And like in the beginning, we have the model-free reinforcement learning, like Q-learning, and different like policy-graded methods, inverse reinforcement learning. And now people start to move to use the model-based reinforcement learning. So they basically will build a model of the robots and then do the reinforcement learning. And recently, like this is like very popular now. It's called the offline reinforcement learning. So basically, the reinforcement learning is like the robot need to keep interact with the environment, and that is also like another disadvantage for the robots, because how do you use the robot to keep interacting with people, with the environment? So that's why people are working on offline reinforcement learning. So basically, it's kind of like supervised learning. You have the data set already, and you don't need the robot to interact with the environment anymore. You just use this data you already have, and then you use the formulation of the reinforcement learning with this data to see if you can achieve like similar results or not. And also here, like the imitation learning, the GAN, all the different methods. And then this is another very popular topic now, the hierarchical policy, especially for, we call it long horizon manipulation. For example, like if the robots will do some, like for example, like making a coffee, then the robots will need to understand like where to grasp the pot, like how to pour the coffee inside, how to serve you. So this is basically, we call it the long horizon manipulation, which is also another very popular topic now. So basically, like after all this, like we basically need to learn this perception, manipulation, and the locomotion policies. The most direct way is we just learn everything from the real world. We need to collect data, train everything with the real robot, the real objects. But also another thing is like we will use a simulation. So we train everything in a simulation. We find the gap between the simulation and the real world, and then we do the sim to real transfer learning. Another method is like, instead of like we want to improve the sim to real learning, we want to improve the simulators, like we build better simulators. This is another direction of the research. So first is the simulation. Like right now, there are already a lot of different simulations for the robots, especially for the deformable clothes. Like for example, this one is Autodesk Maya, which I used before, like we used for the clothes deformation. But for this kind of like Autodesk Maya, all the Blender here, like the biggest problem is this simulation engine are not designed for the robotics. So it's not very easy to actually include the robot model inside the simulation. So you can use this to collect data. You can use this to, just like you asked, like we can use this to decide where to grasp. But if we want to learn the robot motion from scratch, like we want to learn how the robot arm move from here to here, then it's very hard to use this robot. I mean, you can use it, but you need to do like all the robot things yourself. That's why they have like the Unity here. They have the assistive dream, and they also have the soft dream. So this soft dream and assistive dream are all based on the OpenAI dream here. And then here you can easily input the robot model here, and then you learn all the robot policy from the scratch.
Wait, what is the soft gym data actually trying to do there?
This one.
Yeah.
So basically, the soft dream is they just focusing on the clothes, so that's why they call it soft dream. And here are different, like for example, this one is like how they want to fully unfold, how to flatten the clothes. But they have like different applications, like the t-shirts, the bed sheets, like making the bed sheets. But here is like they use this kind of this small ball like the here to simulate the gripper of the clothes of the robots, and they do like how to flatten it, how to stretch it, something like that. And another thing is the Pybolite in the robotics. This is also like a very popular simulation engine in the robotics. And a lot of research has been using the Pybolite. So here are some examples. Like this is like a very classical paper from the Google, like how to do the grasping and also how to do the locomotion. So Pybolite is based on this Bullet simulation engine, but it integrates the Python and the Bullet very well. So like, very popular now. And also the OpenAI gym. This is like especially for if you want to train the reinforced learning. So the OpenAI design is OpenAI gym because they integrate like many different methods, reinforced learning methods together. You can write the easy codes, but to do the training with the reinforced learning. So here are also like different examples. And then in this kind of Pybolite, you can do like one work like we focus on is like how the robot will work with the human. So basically, you can also like input a human model in it. You can design like the height, the weight, the size of the human model, and then each joint is movable. So you can do like different manipulation tasks with the human. For example, this one is like the robot want to do the bathing. So the robot can actually lift the arm of the mannequin and then do the bathing here. This is also like a training process. You can see like in the beginning that like for the reinforcement learning, like the robot will just do random things until they find some good policy. Here are just like more examples, like in this assistive gym, like we have like the feeding, the bathing, the dressing, all different tasks here. Yeah, just play it, but it's fun to watch. Yeah, this one is like we want to, the robot actually want to like grasp the arm and lift the arm. Yeah, and this is like another one, like the mobile manipulation. In the Pybolite, the robot can actually move towards the bed, and in this way you can actually learn not only like the robot arm, how the robot arm do the manipulation, but also how to do the mobile manipulation, because sometimes you need to be closer, sometimes you need to be further from the human. Yes, this is another one, the multi-robot manipulation. This is also like a very popular topic now because there's no need to put all the robot arms in the same robot. We have like several small robots, and they can actually be more like easier and flexible to move in the room. Here are just some other examples. Like for example, the Majuko is like another very popular one for the robot simulation, and it was in the early times like it was not free, like you need to pay for it, but now it's like was bought by the DeepMind and it's totally free now. And also some other simulation from the NVIDIA, like NVIDIA Flex, NVIDIA physics engine. All this one you can have different simulation. So now it moves to another problem is after we have all this simulation, how do we actually collect data here? Like how do we train everything in the simulation and tune with the real robot. So that's why this sim to real problems came out. So there are already a lot of research like focusing on the sim to real. So basically, these are general summarize of the different methods for the sim to real learning now. Like the biggest one, of course, the first one will be the data augmentation, which I'm going to show more, and also about like how to build better simulators for the simulation data, how to use some specific modalities of data to make it easier for the simulation, how to do the adaptation for the different sim to real adaptation. So the first part is building the rich simulators, and this is especially easier for the locomotion because, as you know, like the autonomous driving, they always put the lidars or different cameras on the car, and then they can use the lidars to scan the whole map of the room, like the 3D map of the room, like very easily. So this is like one example of the scanning, and here are more examples like they have the room and how they actually scan the room. You can see like the scanning can have like many like small details. The second one, the data augmentation, it is also like one of the most popular methods now is you have the simulated data and then you want to augment data so it can have a better generalizability. So basically the data augmentation here is like people will usually change, like for example, using this as an example. They want to do some simple task like the robot grasping the object. But let's say if your simulation is like this, and if your real setup is like this, the color is different, the shadow is different, then you will never make it work unless you train everything with the real data again. So what they want to do is like they change different perspectives of the simulation. For example, like they change the color of the background, the table, the object. They change the different position of the robots. They change the camera positions. They change the shadow, all different this kind of parameters. And after that, they will collect a very large simulation data set, and hopefully, like they will learn some generalizability for the robots, and then they don't need to fine tune, or they need like very small amount data to fine tune with a real robot and a real object. This is like the results. So you see, like this is the results like when they trained only in the simulation, and then now they want to grasp the real object. But this is like one of the earliest papers working on the data augmentation for the sim to real learning. So
This,
yes,
what they did work, right?
for the simple tasks
Yeah.
works. Yes, for the grasping, yes. Yeah.
And how early is early?
Sorry.
You said one of the earliest papers. So how early is that?
So this paper is I can't remember, like 2015 or 16 or something. Yeah. I mean, like if you work on sim to real learning, basically if you do this, you never get your paper published again. But at that time, this is like a really good start of this kind of work. This is just like another example, like they work on the car simulation. So basically, again, like they do all different augmentation here and to create the simulation data and test with the real world. So again, as we can see here, they change a lot of like different texture, the background, just to create very large data and tune with the real data. And sometimes they also call this data augmentation as data dreaming. So this is one example. Like they have like the simulation data here, and they do some mask. For example, they have the object here, and then do some mask, and then they put this mask object in different scenarios. So they just put this mask directly in different scenarios to create more scenarios of the robots. And then this is all done. This mask is done in a simulation, but then they put it here so robot can kind of like see more scenarios for the manipulation, and they somehow trying to learn these policies to increase the generalizability. So the third way is how the modalities have a smaller domain gap. For example, like if you work on the RGB images, it's challenging because you have different color, the shadow, the background. So some of them, they will work on the depth images. So the depth images means like you also get one image like this, but for each point, each pixel here, you do not get the RGB value, but you got the Z of the depth value, like how far this person or this like pixel is away from you. So that's what we call the depth images. So because of using the depth images, you only have the this parameter of the depth. So you don't need to worry about the color of the object, the background of the object anymore. And some of the paper, like especially this one, like do the human pose estimation, and they will work on the depth images first in the simulation because it will reduce much more other possibilities for the collecting data in the simulation. And same with the semantic segmentation mask here. So they do not want to work on this whole RGB images, but they want to work on an image with the segmentation masks. Because in the mask, you also you only get like which part is which object. It's much easier to train with the data. So the fourth part is, so until now, like people are working on, like they get the simulation data. They want to somehow reduce this gap between the simulation and the real data. So another group of people working on, they get the simulation data, but they want to make the simulation data to look more real, to make it more similar to the real data. So that's they call it like domain adaptation. So one classical method is using the gun, of course. We have the simulated images. We want to generate some target images which looks like very realistic. And there are actually a group of people like working on that. Like they are using the games to generate the images, like how the car, like the driving in the simulation. Because in the games you can collect a lot of different data, and then they use the gun to generate to make it look realistic, and then test on the autonomous driving. Yeah.
Is this the same as using generative adversarial networks? Or is that different?
It is kind of similar. I would talk about more. So basically like all these methods is based on the gun. So it's kind of similar, but I will give you more examples, yes.
So here you have an image on the left from a simulation.
Yes.
And you make it more realistic.
Yes.
And then you train on the more realistic image.
Yes, exactly. Yeah. Yeah.
Okay. But can't you? So this is just basically making the simulator more realistic.
Yes. Yeah. 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 So basically, it's just another example, like how do they do this domain adaptation. So here are more details, like how do we actually want to translate these images? So basically we have two applications. First one is called paired images. The other one is unpaired images. So the paired images is like, we have the simulation here. Let's say that this is the simulation. We also have the real data, and we want to learn how we can train the network to make the simulation look like the real data. But this is not the usual case, because when you collect the simulation data, you usually do not have the corresponding ground truth of the real data. So the second one is more common. It's called unpaired data. So for example, like here, like you have the input of a horse like this, but you don't have the ground truth of this. You may have the ground truth of this, but when you have the unpaired data, how do you make this simulation data more like the real data? This is something more common, more interesting to work on. So for the paired case, I'll just go very quick with the paired case. This is something like very simple. You can either train with a simple imitation learning to get the loss between the real images and the predicted images, or you can just train the gun to make the simulated images look more realistic. And this is just like a very simple gun here with the loss. These are some examples with the paired cases. So basically, we have the input, we have the ground truth, and with the L1 loss is like a simple imitation learning, and with the GAN and also like how do you combine this together? So these are some results here. And usually, like if you have a very large amount of data, you can see the GAN can generate better images than when you do a very simple imitation learning here. This is some other more examples of the paired cases. And usually in these paired cases, they already have like the open source data. You can easily tune with your own, you can try it with your own method. So this is the unpaired case is something more important. So basically, like let's say you have like two images like this. Like one is simulated images, one is real images. Then how do you train the network to kind of find out the similarity between this? That's why where this cycle GAN is like one of the most popular methods now. Like from the GAN is like you have the generator, you have from the X. Let's say the X is the simulated images and Y is the real images, or Y is the generated images. So you have the generator here, you generate the X to Y, and then you have another discriminator, you compare this Y to the ground truth. But for the unpaired GAN, unpaired cases, you don't have the ground truth. So what they in the cycle GAN is like they just train everything like a cycle here. They have the X, they have some generator, they generate Y here, and then they generate it back to X. And similar to the Y here, they have the X and they have the Y. So basically, they use one GAN to generate the images, and then they also generate it back to compare with the original images there. That's why they call it the cycle GAN. And that's why, so basically that's why in the loss here, like they will have two loss. One loss is the loss for the GAN, like it's just as normal as the GAN, the loss. The other one, it can be like L1 or L2 loss, like when they compare this X hat here to the original X here. But also like they already have like many different methods now, disco GAN or like all different versions of like improved cycle GAN. But cycle GAN is like kind of like one of the earliest works which have like very good results on these unpaired cases. So here are some examples. Like this is like one of the typical results they always show here. Like you have some zebra here, but you don't have like the ground truth of the horse. But somehow they can generate the images to make it look like the horse. Here are just like more examples. Like this is another area like a lot of people working on like different style of the arts. They will also use the GAN to generate like different styles of the paintings, the landscapes.
Sorry, I may have missed something, but how do you train the GAN with unpaired data?
So basically like for the unpaired data, you have like simulated images. You use the generator to generate generated images, and then you have the discriminator to compare, right? For the cycle GAN is after they generate it, they will generate it back to the original one, and they will compare the loss between the second generated image with the original images, and they will also compare this loss.
But so in the unpaired, you have some that are real, some that are generated.
You have the real original image.
Yeah.
You have the generated original image. You compare the loss of these two.
So it's like you're given a horse, you don't know the label, so you take a zebra, then you convert the zebra back to a horse, and then you compare the zebra converted horse with the original horse.
Yeah, so basically like here is like you have two data sets. You have a data set of horse. You have a data set of zebra, but it's not paired. So that's how they learn, like they have like, for example, they have the images of the horse, they generate 2D zebra, and they use the discriminator to compare with the data set of the zebra. But then they also will generate this generated zebra back to the horse, and they compare this generated horse to the original horse. So they have like two laws here. One is loss with the classical gun. One loss is with this generated back horse with the original horse.
But so you can't train on like a data set of horses, zebras, oranges, and apples. Like it's not going to try and.
Well, yes. I mean, if the shape is completely different, it will be very challenging. Yes, of course. Yeah.
Is the gun, is it conditional or unconditional of the guns?
I would say here, like, because you have two data sets, it's kind of like conditional.
Like what is it like in practice, like conditional at that level that like I have like a basic gun. I put noise in and the noise gets packed the way where it needs, but really it's looking like it needs. But the conditional one would take also some like real imaging, or it would be synthetic imaging. That would be like really explicitly conditional. But it would take in also some image.
I mean, yes.
Like any conditional model, basically.
Yeah, so basically, like, while you're trained, you need to give, like, both data sets there as the input.
But, like, if I think about, like, any conditional generative model, let's say text conditional, I put text in, so it takes my text prompt as the condition, but then it also generates some random numbers, and both are taken into the model, and then out comes, let's say, the image, which corresponds to the text prompt. So that would be conditional. That would be so is it also used here? Or
Yeah, it's not like that. It's not like you give like actual condition as the input and to generate something. It's more like you give these two data sets as the input, and you just learn this loss between these two
I see.
data sets.
It's basically like marginalized.
Yeah.
Over. Right?
Yes. And then the next part is after we have all these different methods, like we can use these methods on the robots. So one is this sim to real for the learning the robot grasping. So as you can see here, these are some simulated samples, and these are the real images. So one thing what they do is like they have these simulated images, and then they use this to make these images look like the real images, and then they train everything on these generated real images for the robot policy. And also, like right now, like recently, they also have another paper. Like, if I remember correctly, they call it like reinforcement learning cycle gun or something. So basically, like, they combine the loss of the reinforcement learning with the cycle gun together to train this robot grasping. But I mean, for this kind of methods, I mean, you may get the idea. Like, as long as it's more complicated, the more chance is it doesn't work in other scenarios. So I haven't seen a lot of other people using the similar methods.
Sorry, in the first example of grasping that worked, it was in the simulation you have objects of different colors with different shadows and stuff like that.
Yes.
So in this case, where you go from simulated samples to real samples, like,
Yes.
maybe it feels like you should, from one simulated sample, generate a bunch of real samples with different shadows and different colors and stuff like that, and that may help.
So I think this is like they are working on this from two perspectives. For the first one, like the different color shadow is, they doesn't care about how the real images looks like. They just want to have a lot of data, and they hope somehow this network can learn some policy from that. So that's why they change all the color, the shadow background. And this one is they actually care about how the real data looks like. So they want these images to look exactly like the real images. Although it's not possible, but that's what they target on. So that's why they do this transfer, and then they will tune with a little bit real data to make it works.
Yeah, but it wouldn't help to, from one simulated sample to generate a bunch of real samples that are not exactly the same, that have these different shadows or different.
I would say maybe yes, but for this kind of like algorithm, like usually you have one image, you will generate another images because you already trained the network. Yeah.
On the same question, would it be like here you're trying to make simulated image look like a real one?
Yeah.
Is there any work looking at real sample and making it look like a simulation?
That's a very good question. So actually yes, they do. Like there are a lot of people they work on, this is called sim to real. Some of them, they work on it called real to sim to real. So basically they have the real data, and then they somehow make the simulation, they want to learn something from that and put in the simulation. And then they use the simulation to generate back to the real data. So basically this is more like for example, like they want to learn some dynamics or physics from this real data, and they put it on a simulation. So yes, they have it.
So it's kind of like a disco gap between two elements.
Yes, kind of like that. Yes. Oh yes. So here are just like more examples of these methods. They use like this KUKA robot arm, like which is like a common arm. And they also like keep updating their model. So basically they collect data. So basically what they do is kind of like reinforcement learning, but you don't get the reward. Like you keep collecting data and do the robot training, update the network, and then collect more data like that. So this is just like more details of these methods. So what they did here is like they call it like feature adaptation. So basically you have the image here. They basically have like two laws. So the one loss is like you have the image, the robot grasping, and then you have this loss of is grasping success or not. Or if you output the grasping position or orientation, they will also like the loss of that. And also the domain loss is here is like you have this, and then just like a gun here, like they will update the loss, like if these images look like real or not, and then based on this loss, they will keep updating this sim to real loss here. Yeah, this is like more details about here, like how they train the whole loss. This is like the network they have. And you can see here, like this is like more like a generator and discriminator to see if it's real or not. And another one here is like for this one is called the adapting simulation to real world by learning the dynamic parameters. This is actually similar to what Mohammed asked. Is when you do the simulation, you actually want to get some more information from the real world, and then you somehow improve your simulation. So for example, like this work here, like they are working on like this, putting like they use the robot to open the drawer or hold a string and put the robot in the hole here. But in this kind of like physical manipulation here, you have a lot of different parameters. For example, like the friction of the object, the mass of the object, or the contact between the object and this hole here. So if you learn everything from the simulation like randomly, it's actually quite challenging. So what they do is like they want to learn this kind of parameters from the real world settings first, and then they put these settings in the simulation, and then so their simulation can behave more realistic as the real setup. And this is actually specifically important for learning the deformable objects, because for the deformable objects, you have many different physical parameters. And in the different simulation, you actually have different way to define the mechanism of the deformable objects. So that's why like a lot of other people will working on how to actually learn the physical parameters and from the real data and put it on the simulation. So this is one example from the graph in 2022. They call it diff close. So basically, they want to learn, like for example, the mass, the tension, the stiffness of the different clothes, and then train everything in the simulation. For example, here they want to do how, if you can see here, like they also use this two ball here to simulate the robot gripper, and they want to learn how to actually put on the sock for the human. This is another work from NVIDIA called GradSim. So basically, this is like more straightforward. Like they define different parameters here. You can see the mass, the friction, and then they put in a physics engine. And you can easily change like different physics, whichever physics engine you have. And then they output some states of the deformable object. And usually they use this kind of videos, basically like different frames of the RGB images to present as the states. And then they will have some ground truth data, and they easily compare the pixel loss of each frame of the closed motion. And then they will use this loss to go back to keep training, keep updating their model here. But the problem of this method is you must have the ground truth data for each frame of the clothes. That's why even in this paper, they only work on the simulation, because you easily get the simulation ground truth from the simulation. And that's why a lot of people will also work on like how to actually get the parameters from the real data. This is another method. They use the nerve to do the to do the deformable object simulation. And actually, I put it here is I found it's quite interesting. Like why first time read this paper, because when you're using the nerve, like you may know, like they usually do it like you have one view of the images and you get the multi-view of the images and you have like a 3D model of the object. But what they do is like they even use the nerve on the motion of the deformable object here. So you have the current images, as you can see here, and then you have like either the time or like a motion of the delta x here, and you use the nerve to predict what the object will looks like in the next time step, and then you use on the deformable object here. This one is you may know this one. This is like a very popular one. Using the graph neural network to do the simulation of the water, and then later they also put it on the simulation of the clothes here. Yeah, the video looks a bit weird, but yeah. So now I'm going to my third part, like how to actually use the self-supervised learning for the robots, all the robots in the simulation. You may see this image before. Like this is from the Young and Quinn. Like they were saying, like if the whole machine learning or learning part is like a cake. So the top, this juicy one, is the reinforced learning. So basically, it's like a very fancy topic, but it doesn't do something useful. And the surface part is like supervised learning because it's easy to use. You have the data, you can get good results. But in the most case, like getting the data is always very difficult. That's why the base part, like the biggest part, is requires self-supervised learning to do that. So basically, what is self-supervised learning? So this is one example. Like for example, we have like all different robots here, and we have one image. We want to predict which is this robot. For the supervised learning, you give the ground truth, and you easily train the network to do that. But for the unsupervised learning or self-supervised learning, it's like you don't have the ground truth. You have these images here, and your model or your network or whatever you trained, right? You want to actually have a prediction. Okay, these are the same robot, these are the same, and these are the same. So basically, in the self-supervised learning, is like you will have like a very large data set, and with no labels, which is very common in our case. You have some pre-trained models to do the presentation learning, And then in the presentation learning, you will say, okay, these two robots are from the same class, or they are like looks very similar, and you do the training in the latent space. And then when you have a different data set, you somehow use the knowledge transfer to easily do some downstream tasks, which I'm going to give more details, like how this exactly works.
So in this case, the self-supervised learning is basically a cluster of some sort.
Well, I would say like many cluster methods is self-supervised learning. Not all of them, many of them are the self-supervised learning. You kind of like cluster them in the latent space, yes. So yes, this is just like another explanation, like what is the self-supervised learning. So I use this image. This image is from the also like the slides from the Yellow Queen. So it's very straightforwardly show like why do we use the self-supervised learning. For example, we have the data like this. We can use the past to predict what is next, or you can use some like the future data or the past data to predict what is present. So this is basically like you have the data, and you don't have the label. That's why you use the self-supervised learning. Here are just like another example. Like you have the data set with the no labels, and like you said, like kind of do the clustering in the latent space. So these are like you make the similar data close to each other, and then you do some downstream tasks to predict next. So basically, like I'll give more details of the whole how it works. Like usually, the first part is you have the data. You usually will do some augmentation to make your data set larger. So this is from the image-based augmentation. Like you have the image, you can do multiple things like cropping, changing the color, flip the robot, adding the noise, and you basically say, okay, if I have these images, I do the augmentation to create another images of this. This will be the positive pair. Otherwise, if it's another random image, will be the negative pair. Similar here. From the video-based, you can do also like different ways of augmentation. For example, you can crop some images, some videos. You can drop some frames of the video, and this is also will be considered as the positive pair. And here are also some other ways of augmentation. You can shuffle the order of the frame, and you can also reverse the whole direction of the video, and this also will be considered as the positive pairs. But if you have another video, or this video is not generated by the augmentation from this video, then it will be regarded as the negative pairs. And how do we use these positive pairs or the negative pairs? So usually in the self-supervised learning, like the classic method is called the Siamese network. So basically we have this input 1 and input 2 here, right? We embed them to the latent space here. And this embedding, although they are embedding separately, but they share the same weights of the network. And if we say the input 1 and the input 2 are the positive pairs, and usually this loss will say, let's say it can be 0. Otherwise, we can make a big loss because they are negative pairs. And usually this loss here, we will use this contrastive loss to compute the distance between different states in the latent space to make it closer when it's positive, to make it further when it's negative. So
why it's called Siamese? Because if the network 1 and network 2 were the same networks.
they have the same structure of a network and the same weights, so that's why it's called Siamese network.
But then they were the same networks. Whereas it's just naming.
Yeah.
But were there some other differences in the network? So was it like some piece of the network as the same?
So basically, these two networks will be exactly the same.
Right.
Yeah, same structure, same parameter, same weights, so everything will be the same. Yeah.
But the heads are different, right?
The inputs are different.
Input are different, yes.
So it's,
Yeah.
but it like network 1, network 2, one could think that there's some difference.
Yeah. One most popular self-supervised learning method is called the SimCLR method. So it's basically using the same architecture. Like you have one image here, you do some augmentation to do that, and you project onto the same latent space, and you kind of like calculate the distance. So basically, let's say, to give like a better example, if let's say you have 10 images, like for each image you will augment to another 2 images. So only these augmented images will be regarded as the positive pairs. All the others will be the negative pairs.
But having these negative pairs and not just positive pairs, do they not somehow harm you? Like if you have duplicates of the same image?
Yes, I will show that later. That's a good question. Yes.
Question on this. If the operation, like the augmentation operations that you use, kind of define more or less how two things would be considerably similar, can you not embed that kind of transformation information into your neural network, or like the way you build your neural network, so that it actually learns that an image that has, like, that is just flipped, or like that has symmetry on it, it would improve potentially the more. I don't know if you've got my question.
Sorry, can I say it again?
So the idea is, here you start with a certain image, you do some transformation to it, and then you try and make sure that your model recognizes them as being the same.
Yes.
Can you not embed that, rather than make it a learning process, embed it in the way you build your neural network architecture with like some physics-based, like so embedding the symmetry, for example, as information that it doesn't need to learn. It already knows that an image that is just flipped would be the same image.
Well, I guess yes, but it really depends on the generalizability, right? If you have like very large data, you want to do the different augmentation to make it like robust. Then when you have some new data, because when you have new data, they may not be simple flip or a simple augmentation. They may be another kind of augmentation, but you want to learn this similarity between them.
But then you're kind of biasing your model by imposing the type of operations that you're going to do.
Well, yes, but then usually when they do that, I'm also going to show like how they usually do that. But you need to do a lot of augmentation to make the data as general as possible. Like if let's say, I think you are right. Like let's say if your data is doing the flipping, and then you have another data doing the cropping, and somehow they don't recognize it. Yes, I think you are right. So that's why they need to do a lot of different augmentation. Here are just like different laws of using the self-supervised learning. This is the most typical one, like the contrastive laws. So basically, you have the distance here. You say like, okay, if it's in the same, if it's a positive pair, the distance will be 0. Otherwise, it will be 1. So basically, you make 2 points close to each other in the latent space. If they are positive, it will be further to each other if they are negative. And then later, people will say, okay, this contrastive loss is you only compare one pair. So it doesn't actually describe the relationship from different pairs. So they have this triplet loss here. So basically, you have the data here. You have the positive data. You have the negative. This is all in the latent space, right? So they want to make sure the data between this anchor with the positive should be smaller between than the distance between this anchor to the negative here. But they also have the problem here. It's you somehow only describe these 3 data, the positive and the negative. But you don't describe, if you have another data as a negative here, you actually don't describe how negative between these 2 negative data. I don't know if I'm clear. You say this positive should be closer than this negative, which is good. But if you have another negative here, from these 2 negative here, using this loss, you didn't describe which should be closer to this anchor.
But how would you know which negative should be closer? How would you know which negative should be closer?
you don't know. And also this loss doesn't describe it. So that's why people want to make more changes. Like one of them is, they use this infer NCE loss. This is another one. So basically, like this loss is like they don't just care about like 2 or 3 data. They will care like a batch of data here, and then they use this. Usually, they use some cosine or some other similarity to like giving 2 representations in the latent space. They will calculate this similarity. But again, if this similarity is really accurate or not, you don't know. But you compute this loss and you keep like minimizing the loss to improve this. And similar with this unpaired loss here is like you have like unpaired of data and you compare the loss between unpairs. This is some other like very popular methods now based on the contrastive learning. The first one is called the CLIP. So the CLIP is, especially with the large language model, like very popular now. Like more and more people are using different variants of the CLIP. So the CLIP is like you have the text here, and you have the image here, and you somehow describe it as like different tokens, and you compute the similarity between the text and the image, and you somehow make it pair. Let's say if this, I can't see it clearly actually. So basically you have like one image here, and you have the text here. You can describe, like if this text actually describe this image or not by calculate this contrastive loss here. And another one is called the supervised contrastive learning. So basically they kind of combine the supervised learning together with the contrastive learning. So basically the idea is like the first part will do a simple positive pair, negative pair, and you train with the contrastive learning, and you have the latent space. And then in the second stage, so this is the first stage, is the contrastive learning. And the second stage is like you already have the latent space based on the representations of the contrastive learning. From the latent space, you train another supervised learning to see, to improve the accuracy. For example, this is like one example. Like you have like the data sets of the dog and the cats. So what they claim is like if you do pure contrastive learning, like you have one cat, you augmentation, you train with the contrastive loss. But what they do is better, is like you do that, you get the representation here, and then from the representation you do another contrastive learning. You do another supervised learning, you say, okay, this point in the latent space is actually a dog, and this point in the latent space is actually corresponding to a cat. So basically they do 2 stages of the training. And they claim that this one you can get much better, for example, like classification accuracy using the supervised contrastive learning. The last one is called the contrastive predictive coding, also called the CPC coding. So basically this one is like you have like a series of data. They use it a lot on the videos or the audio. And you have the data, for example, from here to here, right? And you want to predict the future data. So basically they say, okay, like from the time step, like xt minus 1 and the xt, they are close to each other, so they are positive pairs. And you can also set like a closed window. You say, okay, these 3 are positive, and other than, like for example, this one and this one, or this one or this one are the negative pairs. So basically they use this connection on the series of times to construct positive or negative pairs. And then they usually use a series of data to predict like what's the next stage of the data. This is actually trying to, I can't remember, Mohammed, or you asked this. I think you like do the augmentation if it's actually harm the data or not. So basically, this is if you want to make the self-supervised learning works, you need to, this is not said by me, like they are said by many different papers. Like first, you need to have like a very heavy data augmentation. just like Mohammed asked, like you cannot do the flip for the augmentation, and they have another image for cropping. That won't work. You need to do all the different augmentation. The second one is like you need to have a very large batch size, because you have like one. Let's say like you have like the dog and the cat, right? You do the augmentation with one cat. You have two cat images, but somehow in the batch size you may have other cat images. Then they somehow think they are negative pairs, which shouldn't work. So one way to do it is you have a like very, very large batch size to kind of like alleviate this problem. Another one is they call it hard negative mining, or they also call it like device networks. So the idea is like, so originally like you do the augmentation, you say, okay, this is the positive pairs. The cat, the plane are the negative pairs. But somehow in your batch size, you have another image of the dog. So in the original self-supervised learning, you will also consider this a negative sample. So that's why they call it false negative sample. So in this method, it's called debiased SimCLR, like debiased self-supervised learning. It's like you give like another parameter in your loss to guess, like if you have a batch size of 10, let's say, you will guess how many false negative samples you have, and then you remove it. But this parameter, like even in this paper, they said this parameter is you need to tune it. It's not actually learned through the network. Like you need to have like an initial guess. Okay, maybe two of them are the false negative pairs, and then tune it like different times, and you get the better results. And I think until now, like these false negative samples is still like a very popular. It's not a solved problem for the self-supervised learning. Because as long as you don't have the labels, you do not have like the exact information of the false negative sample. And the last part will be some examples of my work about the self-supervised learning for the robotics. I basically will give two examples. Well, I think like Mohammed, I just like know the first example now. Like this is like the part I do the close deformation. So basically, similarly, like I have like the image of the simulated clothes and the simulated mannequin. I want to make it look like realistic. So as I presented, like one way is to use the cycle gun. And this is some results I tried. Although it makes look like realistic, but it also like add or delete some small details, which I don't want. So that's why I work on the physics domain. So basically, I want to learn the parameters of the real garment and input on this simulated clothes to make the whole simulation more realistic. Okay. So this is like a video should like show the clothes dropping. So basically, because we have the simulated images and we have the real images, the difficult part is like how do you actually define the similarity between the simulated and the real images. So that's why here like we actually want to learn this similarity. So in the training data we will use only the simulation data and project onto the latent space. And for the testing, like we have the real data, we will do the one-shot estimation of the parameters of the garment. And we are using the supervised contrastive learning here. So now I'm giving more details. It's weird, like it's doing this, but it should like drop based on the gravity. But anyway, like the first part is like we will collect all the data in the simulation first. So the behavior of the garment will be described as a sequence of the depth images. And here we basically focusing on 6 garment parameters, including the mass, the stiffness, and the friction. But you can easily change different simulation engine, and you can include more physical parameters in this work. And because like we want to define the positive pairs and the negative pairs. So one way I did it is like we will randomly generate some parameters using the Gaussian blobs. And we say like the parameters from the same Gaussian blob will generate like very similar garment behaviors. And they will be regarded as the positive pairs. Otherwise, they will be the negative pairs. And then we project onto the latent space using the infer-NCE laws. And for here, like we have tried using the transformer, ORDCN, and the LSTM. Like in my case, it doesn't make too much difference with these two different embedding architectures. And then after we have the latent space, just like I just present the supervised contrastive learning. From the latent space, I will estimate the parameter residue here in a supervised manner. And when we have the real data, so for the real data, we'll use the robot to hold garment and drop it, and also get the depth images of the real data. We will map onto the latent space using the network we just learned, and also estimate the parameter here. In this way, we can get a one-shot estimation of the real garment parameter. So here are some results. Like here is like, because we have like 100 Gaussian blobs, here is the learned physical representations in the latent space. So basically, the dots from the same color means they are similar positive pairs. So this one is just want to show like the similar pairs will be learned close to each other in the latent space. Otherwise, they will be further away from each other. And here is like when we compare with different baselines. So this baselines including like the simple supervised learning, or like without contrastive laws, or like like the manually tuned method, like different baselines. This one I just want to visually and quantitatively show like this contrastive learning has the best results. So basically here is the depth images of the real garment. Here is like we use this method to learn its physical parameters and put it in the simulation. And this is how it looks in the simulation. And this is some other baseline. So basically, want to show here like this method has a similar deformation as a real garment. And basically, like another thing is like we are extending these methods not only on the clothes but on all different data sets. So basically, we already have like different public data sets from, for example, the fluid dynamics from DeepMind, some closed data set from MIT and Stanford. And we are also using the event camera here. I don't know why that video doesn't work. So basically, like this is like one example of the event camera. Like in the event camera, it doesn't take the frames and frames of RGB images. But if you take the brightness changes of each pixel, so as long as like there's moving object, like the brightness change of each pixel, it will detect an event here. So basically, like for some like high motion movements, like the clothes dropping, you can get like better results with the event camera. This is like some results here. So basically, like when we use the this data set called flag in the wind. So basically, it has different flags. They have different wind of the speed, speed of the wind, and basically we use this debiased SimCLR here to project on the latent space. And you can see here, like the darker the color means the speed is the wind speed is higher. So it's basically kind of like clustering this high speed wind here and the low speed wind here. And also like when we use the RGB and the event cameras, like the event camera gets much better results. Because in the event camera, like you don't need to care about the color, the background of the flag. So this is another work I want to present. This is like a new work, like we are doing something not very robotics. like I said, like we collect the data of the human dancing, and we use the self-supervised learning to give the feedback for the dancer. So basically, like for the different people, they may have like different dancing motion. So like we have the expert dancing motion, we have some like beginner dancing motion. And this is how the skeleton looks like in the motion capture system. Because in the motion capture system, it doesn't take the RGBD images, it will take the whole skeleton of the human motion. So basically here we can do like different downstream tasks. We can do the human motion analysis, we can do the action quality assessment. So the action quality assessment is like we give the feedback, is this like the beginner level of the dancing or the expert level of dancing. And also we do the skill determination, like for example, we will give like very detailed feedback for the user, like which motion needs to improve. It's like the leg motion or the arm motion. So basically, we also use the self-supervised learning model here to give the feedback of the downstream tasks. This is our network. So basically, we have like the motion of the human dancing data. We also have the data of the music here. And also we do the augmentation here, and then we project onto the latent space. And when we have the real data here, we will also map onto the same latent space. And then we can do some downstream task here to do the prediction. And also here, for the motion data, we use the STGCN, and for the music data, we use like a simple ResNet 18 works. So basically here the Siamese work, these are the similar. We have the real data, we do the projection, we do this. So basically like we collected two very large data sets. Like the one data set is our own data set, we call it dance music level. So basically we have like 20 different dancing musics. We have like different genres of the dancing. We have like 900 frames in total for all the dancing. So basically we have different music here, we have like different level of the dancing data. And we also test our methods on another public data set called AST++. This is another public data set. They also have like a very similar setup, but it's just like they are focusing on one level of dancing, and they also have like different genres and different dancing musics. So basically, this is our setup. Like as you can see, we have all the cameras here on the truss for the motion capture system, and usually we will clear the room while we collect the data, so that people can dress the motion capture suits and then do the data collection. Yes, here are just some like videos I want to show like how we actually collect the data for different dancing, different level. Anyway, like here are just some results. Like for example, here we can classify different genres of the dancing into different places in the latent space. And here is like another very interesting result is because for each person we ask them to dance 100 times, and this 100 times is like lasting around 3 months. Like they will dance the same music. But in the beginning, like they will dance like relatively not good. But then because they dance 100 times, they are doing better and better. And here are actually like some results to showing like in the beginning, like their dancing can be like when we do this downstream task, like their dancing can be classified as the beginner level, but later is intermediate, and then later is as the expert level. So basically, it's funny to see like this is something we didn't expect in the beginning. Like we can even see the whole progress of like one random person start to learn the dancing and how it does. But again, like we are dancing some. Each person are dancing some like very simple motions, like not professional dancing. Here are just some other examples. Like we have like the dancing data. So here, like we have different genres, jazz, the K-pop. We have different level, beginner, and all with the self-supervised learning, it clusters quite well in the latent space. Yes, basically that's my talk. Thank you.